Welcome everyone to today's lecture on advanced topics in networking. After we introduced peer-to-peer overlays last week, today's lecture is going to cover a specific overlay architecture, namely distributed hash tables. So let's get started right now. First, we're going to introduce the topic by discussing distributed management and retrieval of data in general. Then we're going to talk about the fundamentals of DHTs, and then we'll look into DHT mechanisms, and finally we summarize this topic and gonna look at the specific example of DHT algorithm, namely Chord. First, let's start with a general introduction. So the essential challenge in most peer-to-peer systems is that someone has an item D to offer and asks himself where this item should be placed. And on the other hand, there are people that are interested in this item D and are wondering where they can actually find it. So the underlying issue is where these data items can be stored so that they can be easily found. Of course, this has to happen with scalability in mind, so the complexity for both communication and storage of these items need to be kept in a scalable manner. And also the robustness and resilience are essential here, especially in case of faults and changes of the underlying topology that may happen frequently. Now let's compare different strategies how data retrieval can be done. We already had taken a look at some of these possibilities in the last week lecture, where we looked at the central server-based approach, namely Napster, and the opposite approach, the flooding-based search with the Gnutella network. And today we'll also take a look at a more structured approach, namely distributed indexing. So let's review these different strategies now. The most simple strategy is a central server-based approach. Here we have a server S, for example, that stores information about a node A that stores an item D. This requires that node A announces basically that it stores this item for others who are interested in it to look up this information. So in a second step, then a node B, for example, who is interested in this item, just needs to request the server S for the location of that item D. And then the server S will tell B that in this case node A stores that particular item D, and then node B can request that item from node A directly. Now, the advantages of this approach is that the search complexity is constant. So you just need to ask the server, and then you have the answer very quickly. Now, another benefit is also that complex queries and fuzzy queries are possible in this case, and it's a simple and fast approach. However, there are also a number of problems with this approach. First, this approach doesn't really scale because the state in the server will grow with O of n, n being the number of nodes in the system, and also the network load and the system load of the server will increase in the same manner. Additionally, the server also determines a single point of failure or a single point of attack. That means also for lawsuits that are intended to bring down the server, potentially for illegal storage of illegal content. Another problem is that the maintenance cost for operating the server are increasing in a non-linear manner. So of course it's possible to achieve a high availability and scalability, but that always comes at a certain cost. So especially for systems with massive numbers of users, this type of central server-based approach is not really suitable. But overall, for many applications, especially small and simple applications, this is still the best principle. Now let's look at the other extreme, which is the flooding-based search. This is a fully distributed approach based on the motivation that, as we just saw, central systems are vulnerable and do not really scale. Now, in the fully distributed approach, also called the unstructured peer-to-peer approach, we follow the exactly opposite way. Here we store no information on the location of content at all, and the content is only stored in the node that actually provides it. In this case, data can be retrieved as follows. First of all, since there is no routing information for content, it's necessary to ask as many systems as possible, or as many as necessary. And the approach here is to basically flood those queries, which of course results in a high traffic load on the network and therefore doesn't really scale. A better approach is to do a highest degree search. So in this case, large areas are quickly searched through, and that then can optimize the amount of traffic load that is necessary to quickly find an answer to a particular query. Now, here's an example how this flooding-based search works in a fully decentralized manner. So there's no information about the location of data in any of the intermediate systems at all, and so there is a necessity for a broad search. In this case, we have node A that stores an item D, and node B that is interested in this item, and so node B, which acts as the requester here, asks all its neighboring nodes for that item D. These neighboring nodes then forward that information to their neighbors, and so on, until eventually this request arrives at node A, and then node A can answer directly that it has the particular item D available and can offer it to node B. Now, we have seen two extreme approaches: the central server-based approach, that where the node state increases in O of n being the number of nodes in the network, whereas at the same time the communication overhead is constant. That means you only need to contact in one hop this central server. On the other hand, the flooding-based approach has a huge communication overhead. But the node state here is constant. That means you only need to store that information on the node that actually provides the corresponding data. Now, the question is if there is a scalable solution that somehow takes the best of both worlds, so that scales both in terms of the node state as well as in terms of the communication overhead. And indeed, this solution exists, and the approach that achieves that are the distributed hash tables. Distributed hash tables scale with O of log n, which is scalable because the more the size of the network n grows, the less the additional overhead or node state increases. There are no false negatives. We'll see later what that exactly means. And the distributed hash tables are also resistant against changes. That means, for example, failures in the network or attacks against the system, and also short-time users that quickly join and leave the system again typically don't create a huge impact on DHTs. Now, let's look at how scalability actually is achieved, or what it actually means. So we achieve with this DHT-based approach scalability in two dimensions. First of all, in the communication effort. That means only O of log n hops are required to reach the particular item, and also the node state needs to scale, that is the number of routing entries that each and every intermediate hop needs to store in order to be able to forward queries in the network. This is illustrated here also. So if we have a requester that is interested in a particular data, then this data is typically mapped with a hash function to a specific ID, as we will see later on, and then a number of routing hops are required, as mentioned, typically in O log n hops, until the actual node that is storing the data is reached. And every node in between needs to store an amount of routing information that is links to other nodes in the network that helps then to forward those queries until the final node that has the information is reached. Now, in order to achieve that, there is an underlying approach that all the DHTs have in common. That is that the data that is stored in these systems and the nodes that are helping to maintain these systems are mapped into the same address space. And the intermediate nodes that are responsible for forwarding the corresponding queries until the final nodes are being reached, the target nodes are being reached, need to maintain routing information so that the forwarding of those queries to the respective destination, in this case the destination is a specific content or data item, not a location as such, can be reached efficiently, and a definitive statement about whether or not that content exists can be made. This, for example, is different in the flooding-based search because if you have not been able to reach all the nodes in the flooding-based search, you can never be sure whether you've actually reached all the nodes that potentially have the corresponding data, and you can never give a definitive statement about whether or not a particular content item exists in the network. Now, distributed indexing, or the DHT based approach in more general, also has some problems. Mainly that the routing information that is necessary to route queries in the network need to be maintained. It needs to be updated whenever the network changes, for example, when new network join the system or when some nodes leave the network. Additionally, also fuzzy queries, that means, for example, wildcard searches, are not generally supported. They can be supported, but that requires additional mechanisms that can become quite complex. Now let's compare the different lookup concepts. We've looked at central server-based systems where the node state increases linearly, whereas the communication overhead is typically constant. Here, fuzzy queries and definitive statements about existence of content can be done, but the system is not very robust because it's basically a single point of failure. In the flooding-based search, the node state is constant because only the nodes that have the information need to store it, whereas the communication overhead increases tremendously, basically with O of n square. Fuzzy queries, however, are possible here, and the system can be considered very robust because any node can leave from the network without any issues. However, it's not typically possible to give a definitive statement about the existence of a particular content item. Now, distributed hash tables take the best out of both worlds. They scale with both the node state and the communication overhead, but they typically do not support fuzzy queries. However, false negatives do not exist, and the system can be considered robust because any node in the distributed hash tables can leave from the network, and the network adapts itself to those changes. Alright, now with this introduction, let's dive into the fundamentals of distributed hash tables. There are some challenges for designing DHTs. First of all, the characteristics that we want to achieve are, of course, that these DHTs can be flexibly used for different applications, that they are reliable, and that they scale, as we've just discussed. Also, we want to ensure that the content items that are being stored in a DHT will be equally distributed among all the nodes. Because if, for example, one single node would take care of indexing all the available content items in the network, then we end up again with a central server-based approach or a single point of failure. So this equal distribution is very crucial for robustness and also for efficient lookup of the content in the network. Another key requirement is that whenever network links fail, or whenever new nodes join, or when some nodes leave from the network, that the system permanently adapts itself to these changes. And so whenever new nodes join the network, for example, responsibility needs to be assigned to them. So for example, they need to become responsible for certain new content items in the network. And when these nodes fail or depart from the network, these responsibilities need to be reassigned and redistributed among the remaining nodes in the network. Now, another underlying concept that is included in the name distributed hash table is the concept of hash tables. A hash table essentially takes a particular input, X in this case here, hashes it, and then provides a result. Now, the hash function also does a modulo operation, modulo n here, where n is a fixed size. Now, if n eventually should be changed, then that means that an entire remapping of these outcomes need to be done. So the result basically changes in this case. So n needs to be selected very carefully. Because the remapping, when it would need to be done, is very expensive in a DHT. Now, in a distributed hash table, the fact is that every node in the network takes a part of that hash table and stores corresponding information. So nodes become responsible for particular intervals of hash values that are calculated with these hash functions. And the more peers that participate in this, the smaller the intervals become for which these peers are responsible. Now, there is a sequence of operations necessary for this to be able to be implemented. First of all, as mentioned earlier, the nodes and the data items need to be mapped into the same address space. So to achieve this, peers and content items are being addressed using flat identifiers. And there's a common address space determined that is valid both for the data items as well as for the nodes in the network. Then the nodes become responsible for the data that falls in their part of the address space, and data items that will be stored in the network need to be associated to those nodes, and these associations can change because nodes may disappear from the network or new nodes may join the network. Once this mapping function has been determined, basically data can be stored and looked up in the DHT. And now search here means that actually a query is being routed to the responsible node that is then able to answer the corresponding query. This node that is responsible for that data item may not necessarily be known in advance, so you only know it once the query gets closer to that node, and then that responsible node is able to make a definitive statement about whether or not that particular data item that is queried for is available in the network. Now let's go through these steps. So first of all, the mapping of content and nodes into a specific address space. Usually we use a sequence of bits, typically M bits, where M can be 128, and so the address space goes all the way from 0 to the maximum size, that is 2 to the power of m minus 1. And this is selected such that 2 to the power of m minus 1 is much larger than the actual number of objects that we wish to store in the DHT. Then the data items and the node items need to be mapped into that address space, which happens with a hash function. So for example, if we have a string like my data that we would like to store in the network, then we hash it and calculate this modulo 2 to the power of m, and then we get a result, in this case here 3107, that then determines the actual location of that data item in the address space that we have defined. Now the nodes that participate in this need to be mapped to that address space as well, and then become responsible for parts of that address space. So you can see here several nodes that are basically located in that address space. Often this linear space is viewed as a circle, as it's illustrated here. And we have, for example, node X here that is mapped with that very same hash function and has in this case address 2906, and we have a node Y here with the address 3485, and then the data item that we have calculated here as an example just falls in between those two nodes. Now it depends on the DHT which of those nodes now actually are responsible for storing that data item. It can be either, for example, the node that follows that number, or it can also be the node that is most closest to that particular item numerically. Now, this is a very important concept in DHT, that basically the address space needs to be associated with the nodes, and so that each node essentially becomes responsible for part of the value range to which these different data items that are stored in the network will be mapped to. Now this happens often with redundancy. That means those parts can actually overlap with each other, so that more than one nodes are in fact responsible for a particular data item. And as mentioned, this needs to be continuously adapted, because nodes anytime may join and leave the network. Also, another observation is that the real underlay of the network, as illustrated here at the bottom, and the overlay, that is essentially a logical network, a logical topology, are often uncorrelated with each other. So whatever is a neighbor in the overlay is very rarely a neighbor also in the underlay network. Now this was the first step of mapping the nodes and data items in the actual address space. Now the second step, as mentioned before, is the actual location of a data item. This is essentially a routing mechanism that routes a particular query to the corresponding key value pair that a particular node is interested in. So here in this case, we have a requester that is looking for the data item my data, and so what it does is it applies the hash function and then gets a number, in this case 3107, that the DHT routing mechanism needs to forward the query to. The requester can start at any arbitrary node as initial node, and from this node, which here in this case is 611, the query is then routed until eventually the responsible node is found. In this case, the DHT is organized such that the node that follows the corresponding key 3107 is responsible for that data item, and in this case this is the node with the ID 3485. And so in this case the node with ID 3485 then stores the particular key value pair that in this case is the number 3107 as key, and then as a value basically either the data item itself or a pointer to the location of the data, for example an IP address and port number of a node where the actual data item can be found. Now there is two approaches in which content can actually be retrieved. So one option is that the key value pair is directly delivered to the actual requester, and then the requester analyzes the key value pair tuple, and either that already includes the actual value that the requester is interested in, or in case of indirect storage, the requester then uses the IP and port address from which the actual data item can be retrieved. Especially for large data items, it's more useful to do that indirectly, because otherwise, whenever the network changes, these large data items would essentially need to be moved among the nodes, which can be a very costly process. And that is exactly explained here. So how the content is actually stored is up to the application. So the DHT just maps the data that is identified with a particular string, in this case my data, to a number that is then an address in the DHT address space. And in case of direct storage, the actual value is contained directly on that node that is responsible for this key. Now for large content this can be very inflexible, but for small amount of data, like data items that are less than 1 kilobyte, this is typically okay. But for larger items, the indirect storage is more useful. In this case, the value doesn't include the data item itself, but instead just includes the actual storage address of the content, which, as mentioned before, can be an IP address and a port number that refers to a node from which the content item can then be retrieved. This is much more flexible. The only drawback here is that we require one more step to reach that content, because we first only get the IP and port number or whatever refers to the actual content, and then we need a separate step to retrieve the content from that location. All right, now after having discussed the basic fundamental of DHT algorithms, let's look at some specific DHT mechanisms. First of all, let's look at how DHT deal with the changes in the network in terms of a new node that joins the network. First of all, that new node needs a node ID. This node ID can be calculated either based on a random number or, for example, on the node's public key, from which then the node ID is being retrieved, for example, based on a hash function. Then that new node contacts the DHT network via any arbitrary node, which in this case is called the bootstrap node. And based on that initial contact, the new node then looks up its own node ID in that network. And based on that, the new node then gets a particular hash range assigned to it. In this case, the node gets the address 3485, and so it finds its own location and thereby its particular hash range for which it is responsible will be responsible for after contacting the node with the address 2906 as the bootstrap node. Whenever the new node has found its location, it then also needs to copy the key value pairs that are falling in that particular hash range. And as we mentioned before, that often happens with redundancy, so it will not be the only node that is responsible for these items, but it will just take one copy of those key value pair in its range so that it can help answering queries for exactly those keys. And last but not least, the node also needs to bind itself into the new routing environment. That means it needs to notify the neighbors about its existence, so that it will also be used to query to route queries in the network. Now, whenever a node departs from the network or fails even, a number of additional mechanisms need to take place. Now, of course, it can always happen that nodes actually fail, either because of power failures or because of other reasons. Now, in this case, it is not possible to copy the key value pairs before the nodes are actually leaving, because failures, as it's in their nature, happen very suddenly. And so in this case, only redundant key value pairs can actually help to maintain these key value pairs available. Also, the routing paths that then need to route around those failing nodes need to be in a redundant fashion. There need to be alternative routes in this case, and we'll see later on how that can work. At least if one copy of a key value pair still remains in the network, a DHT usually allows that these key value pairs are still retrievable. Now, a nicer way of leaving the network is if a node is departing. That means it first of all notifies the neighbor nodes, that it is going to leave, and so the hash range can be partitioned before that node actually departs from the network. Also, the key value pairs that it was responsible for can be copied beforehand, and then only the node actually unbinds itself from the routing environment. Now, after looking at these fundamental mechanisms of joining and leaving nodes, let's summarize that all up. First of all, let's look at how DHTs in terms of interfaces can be used by applications. There are three basic methods with which applications can interact with DHTs. First of all, to provide information to the DHT, that means store actual key value pairs. Um, we use the put method that essentially requires a key that is a hashed value of the description of the data, along with its value that can be either, as mentioned, an IP address and port number or the actual content itself. Then to request that information later on, that means to search for that particular content item, there is the get method that takes just the key as a parameter. And this get method then results in a response that then includes the actual value that is associated with that key. Now, as long as DHT distributed hash tables follow this generic interface or these generic methods, they are interchangeable with each other. So you can basically take any DHT implementation, be it CAN, chord, pastry, tapestry, or any other DHT, as long as this generic interface stays the same, we can just replace them without actually replacing the application or changing the application that makes use of it. One example of a DHT that we'll discuss today is the chord DHT. Now, summarizing the properties of DHTs, we basically use routing information that is stored in any of the intermediate nodes to efficiently search for content through a large network. And we define keys that are associated with the particular data items that ideally are evenly distributed across the nodes of the distributed hash table. And in this way, we achieve essentially a distributed index with no bottlenecks, where also the number of stored keys can continuously increase, and even when nodes fail, this doesn't immediately crash the entire system, so we can tolerate individual node failures, and also attacks against the network can be survived. The system is a self-organizing system, so any node can join and leave from the system, and the system adapts itself to these changes. And typically, these kind of DHTs can be realized quite simply and efficiently. And they're also flexible enough to support a very wide spectrum of application. And application basically defines the semantic meaning that the keys have, and also the value that then is included or associated with these keys very much depends on the application, be it an IP address and port number, be it some metadata, or even more specific application specific information. Now, different DHT implementations exist. Some examples are outlined here. Pastry was one of the first ones being developed at Microsoft Research in collaboration with Rice University. Chord, which we'll discuss today, was developed at UC Berkeley together with MIT. Then Tapestry was another approach developed at UC Berkeley. Also CAN. This is a two-dimensional or multi-dimensional approach and differs a little bit from, for example, Pastry and Chord. And then also pgrid, which was developed at EPFL Lausanne in Switzerland. And there are plenty of others, for example, Kadimlia, which we'll look at in the next lecture, Symfony, Visura, and many more. Alright, now finally let's look at the very specific DHT example, namely chord. And we would like to look at how the chord topology looks like, how routing is being done, and how the chord network self-organizes itself. First of all, let's look at the identifiers and topology in the chord network. So in chord, there are L-bit identifiers. That means identifiers are integers in the range starting with 0 all the way up to 2 to the power of L minus 1. These identifiers are derived from hash functions, typically Shannon 1, and there are key value pairs that are being stored. Now let's look at how these key value pairs can be stored. If we do that by choosing the successor of a particular ID, then in this case where we have 3 nodes in the chord network, 0, 1 and 3, basically successor would mean that 1 would be responsible for the key with ID 1. Then for the key with ID 2, the node with ID 3 would be responsible because it's the successor of 2. And for example, a key with identifier 6, the successor would be 0, node 0, and so node 0 would store that particular item. So if we define here the responsible nodes, we can see which range of address space these 3 different nodes are essentially responsible for. And that's exactly how it is defined in the chord network. Now let's look at how routing can be done. The simplest topology to do routing in a chord network would be to define a circular linked list. That means each node has a link to the clockwise next node. For example, node 0 has a link to node 1, node 1 has a link to node 3, and node 3 has a link to node 0. A primitive routing would then look as follows. So when we want to search for a particular key with ID X, then we would just forward the query in that circular linked list until the successor of that key X is being found. And then the result of that query can simply be returned. The benefit is that this is really simple, and also the node state in all the nodes is constant because they just need to store one link to the next node. However, the drawback is that the lookup efficiency is really bad because on average we need to basically go through half of the nodes until we found the result for the actual query. And if there is one link that breaks, then the queries cannot be forwarded anymore, and so that will potentially then break the entire system. Here's an example of how that simple routing algorithm can work. If we look for a key with ID 6 and we start with that query at node 1, then node 1 would forward that to node 3, and then node 3 would forward that to node 0, which can then provide the answer for that particular query, namely node 0 that is responsible for that item. Now let's look at a more advanced type of routing mechanism for the chord network, in which case we store multiple links to the Z next neighbors. In this case, queries can be forwarded in a more smarter manner, namely to the farthest known predecessor of K. Now we can take that to the extreme and just put z equal to n being the number of nodes in the system, and then we basically end up with a fully meshed routing system. In such a case, the lookup efficiency is really good. We have a constant lookup efficiency because we just need one hop, and then we find the result of a particular query. However, the node state in this case increases linearly because we need to maintain links to all the other nodes in the network. And so the scalability in this case is still poor. A more scalable routing is, as we just saw, because linear routing basically scales poorly, with a mixture of short and long distance links, so that we can accurately route whenever we get to a node's vicinity, but at the same time also have fast progress over large distances, so that we very quickly get into the node's vicinity, where then the queries can be routed more accurately. And we need to ensure here also that the number of links that every node needs to maintain to other nodes is bounded, so that it doesn't increase beyond limits. And the way that Chord achieves that is with an approach that is called finger table, and you'll see why it is called finger table. Basically, every node stores such a table, in which it contains log of n links to other nodes, n being the number of nodes in the network. And those links basically cover exponentially increasing distances. That means for node n, its entry I, that is the row I, the row I in its table, points to the successor of n plus 2 to the power of I. This is also called the eth finger of that particular node. So let's look at an example here. If we look at the finger table of node 0, then n is 0, and 2 to the power of I can be calculated. So first I is 0, 2 to the power of 0 is 1, so that means that we start with 1, and the successor of 1 is node 1. Then next I is 1, so 2 to the power of 1 is 2, and the successor of 2 in this case is node 3. And next with e equal to 2, we can also calculate the successor here. The successor in this case is is the successor of 2 to the power of 2, that is 4, and so the successor of ID4, if we look at the network topology here, is node 0. And we also see here the key that is currently, the key value pair that is currently stored with node 0, which is the key 6. Now we do that for all the nodes in the Chord network. Here we have the finger table of node 1, where equally we define the successors according to the function that is shown here. So we start with n plus 2 to the power of 0. N here is 1, and 2 to the power of 0 is also 1, so we start with 1 plus 1, that is 2, and the successor of 2 is 3. So we end up with a link to node 3. Next, 2 to the power of 1 is 2, plus n equal to 1 is 3, and so the successor of 3 is again 3. And next, 2 to the power of 2 is 4, plus 1 is 5, and the successor of 5 is node 0. And so that determines the finger table of node 1. And we do the same also for node 3, in which case the successors of all the fingers end up pointing to node 0. Now let's look at a bit larger chord network here, and let's look at how the routing algorithm works in this case. The basic definition of the routing in chord is that every node n forwards the query for key k clockwise in the network. And it does so by sending the query to the farthest finger that precedes k. And it does so until n is equal to the predecessor of k, and the successor of n is equal to the successor of k. And if that last condition is met, then we have found the successor of n, and so we can provide as a result the source. We can provide that result to the source of the query. So let's look at an example. Here we are interested in key 44, and we start at an arbitrary node, in this case node 52. Node 52 has the following finger table, and thus sends the query for key 44 according to its finger table. It does so by looking up the furthest finger preceding k. In this case, the farthest finger that is still smaller than 44 is node 23. So it forwards that query to node 23. Then node 23 also looks at its finger table and again forwards the query to the farthest node preceding k, that in this case is node 39. And then we look at the finger table of node 39, and node 39 now has a link both to node 42 and node 45. Node 45 is succeeding node 44, and node 42 is the farthest node preceding node k. And so in the last step, we now found a node that is the predecessor of k, and the successor of itself is actually the successor of the key as well. And so we have found the responsible node for this key with ID 44, which is node 42. And so this answer is now returned to the source of the query. Now, as we mentioned earlier, this DHT completely self-organizes itself. That means whenever changes happen in the network environment, those are handled accordingly. That means, for example, when nodes fail, or when entire network links fail, or when new nodes join the network or depart again from the network. In all of these cases, a consistent system state needs to be maintained for routing. That means the routing information on the intermediate nodes need to be kept up to date so that the routing can be done correctly, and so the correct successor information can be retrieved. Also, the efficiency of the routing very much depends on the fact that the finger tables are correct. So that's why these informations need to be consistently maintained. Also, for all these operations, there needs to be a failure tolerance, so that whenever individual nodes or individual links fail, that we can still reliably retrieve the corresponding results. Now let's look at how failure tolerance is being included in the chord network. So there can be finger failures during routing. That means query cannot be forwarded to a particular finger. And now in this case, what happens is that the forwarding is just simply done to the previous finger. That means we ensure that we don't overshoot the destination nodes. While doing so, at the same time, a repair mechanism needs also to be triggered in order to replace the finger that has been failing with a successor of that particular node. And so that is done actively. Every node periodically checks the liveliness of all its fingers, and then when it finds failing nodes, it just replaces them with correct nodes. Now, this can be done very frequently and thereby increases maintenance traffic, or it can be done less frequently, and then correctness may potentially be decreasing. Now let's look at how this correction can actually be done in case of failing fingers. So as mentioned before, we had a query that we wanted to look up, and the query was sent here in the first step to node 23. Then node 23 forwards it to node 39. Now in this case, node 39 is failing, and so we need to find an alternative node to forward the query to. As mentioned here, we forward in this case the query to the previous finger, that is node 33. So because node 39 is failing, we send the query to node 33 instead. And then node 33 looks at its routing table and then finds that node 42 is the farthest node, again according to the routing algorithm that is preceding K, and then sends the query to that node. And as you can see, the number of routing hops actually even stays the same. We don't even increase the number of hops that are required until the corresponding result is being found. Now, another thing that may happen is that we have a successor failure during routing. That is, in the last step of routing, when we actually want to return the node that is responsible for a particular key to the source of the query. And so in order to ensure that we can still retrieve the corresponding key value pair, we need to store not only the first successor, but we need to store n successors in an entire successor list, so that when the first successor, that is successor 0, fails, then we can just use the next successor, successor 1 in this case, and so on. And in this case, the routing will only fail if n consecutive nodes fail simultaneously, which would be a very rare case. Now, n in this case can be adapted depending on how many nodes we assume may actually fail simultaneously. And this successor list also needs to be actively maintained. This happens through periodic checks similar to the finger table maintenance, and is of course very crucial so that the correct responses can be returned to the source of the queries. Now finally, let's look at what happens when new nodes arrive in the network. This new node first needs to pick up an ID that can be either based on a random ID. Here it is assumed that with this approach the node IDs will be equally distributed, but in fact that is not necessarily guaranteed depending on what type of random generator is being used. Then the corresponding alternative is to use the node's IP address and port number and then feed that into a hash function, which results in an identifier. Or we can also actively place the new nodes, for example, based on the load of the existing nodes, so that the new node falls in an area where currently a lot of load exists, and so it can easily help taking over part of that share of the load. or it can be also done basically on geographic location, for example, to ensure that the overlay network is mapped more closely with the actual underlay network. Now, once a new node ID has been picked, that new node needs to contact an existing node that it uses as a bootstrap node. This can happen either with a controlled flooding based approach or by using a DNS alias that points to a particular node, or by simply going to a website that then publishes existing nodes participating in the Chord DHT. Now here we choose a random identifier, in which case the new node gets the ID 6, as shown here in the topology. The new node then falls into that address space with ID 6, and then the actual existing node is being looked up with a DNS alias. The DNS name that is used for this is entrypoint.chord.org, and an IP address is then being returned from the DNS system. With this IP address, the new node then looks up this existing node that in this case here points to node 1 in our Chord overlay. And node 1 is then being used as the bootstrap node for that new node to join the network. Next, we need to construct the finger table for that new node. This happens by iterating over the individual finger table rows. And for each row, we basically need to place a query in the existing network with node 1 as the bootstrap node, where we look for the successor of that particular entry. And we can just use simple standard chord routing to look up this information from the existing Chord DHT. Next, and so that is happening here with this example, we see that we need to just look up basically the 3 successors of ID 7, ID 0, and ID 2, following the mechanism that we have described earlier. At the same time, we also need to construct the successor list. In this case, we have basically 2 successors, and the 2 successors, we retrieve them from the successor list of our own successor, that is node 0. Yeah, the successor of node 0 are node 1 and node 3, and so we take from that successor list just the first successor, that is node 1, together with the node 6 own successor, which is node 0, and that then becomes the successor list of node 6. Now, finally, we also need to retrieve the key value pairs so that the new node takes the corresponding share in keys that are stored in the network. Now, according to the definition, every node is responsible for all the key value pairs that for which its own node ID is essentially the successor. And in this case, the key value pair with ID 6 that is currently stored at node 0 now is newly assigned to the new node 6. And so the key value pair with ID 6 needs to be transferred, in this case, to node 6. Now, let's summarize the basic Chord characteristics. First of all, looking at the complexity, it's so that the number of messages that are necessary for looking up key value pairs in the chord network increase with O of log n. Also, the amount of storage that every node needs to maintain to forward those queries increases with O of log n, where n is the number of nodes in the network. And there is also a management overhead that is necessary whenever nodes join or leave the system, or for example also fail and therefore ungracefully depart from the network. And this overhead increases with O of log square n in the network. This is a bit worse than the message and memory overhead, but since these management actions don't happen very frequently, they basically only happen whenever new nodes join or leave, this is tolerable. Advantages of the chord network are that there exist actually theoretical models and proofs about this complexity, and yet the network stays really simple and flexible so that it can be used by different applications. On the other hand, there are also some disadvantages, namely that there is no notion of node proximity or proximity-based routing that can be used for optimizations. And also it can happen that, for example, the chord ring may become disjoint in realistic settings where links can arbitrarily fail. There have been many improvements of the chord network, for example, to take proximity into account, and also by considering bidirectional links so that link failures can be more easily adapted to. And also there have been improvements in terms of load balancing to really ensure that data items in the chord network are equally distributed among the nodes. All right, that concludes today's lecture on DHT. Thank you very much for your attention, and looking forward to see you for the next lecture. Thank you.